So, getting started on circumcenters and incenters, the whole big thing is that it connects directly to what we did the last time. So what we did the last time was perpendicular bisectors and angle bisectors. You're going to see as we look through this, what we're going to talk about today is going to tie directly to those. Before we get to that, the first definition is going to be concurrent lines. Guys, when you have two lines that intersect, they're called intersecting lines. Okay, their point is called a point of intersection. It's a single point narrated by 2 points intersect. When you actually have a third one go through that same point, they're actually called concurrent lines. They create something called the points of concurrency. The point of concurrency. Guys, they're concurrent lines. They hit at a single point. It's called the point of concurrency. That point of concurrency, there are 4 different ones that you're going to get. Listen, there's 4. You've got to make connections between what goes with what. The first one is going to be for perpendicular bisectors. If you need to do something so that you can see this, so that you do not, you've got to get what's important here. Perpendicular bisectors. So when you see those congruent symbols on either side and you see those right angle symbols, those are perpendicular bisectors. Right? And anytime you see those perpendicular bisectors, they are going to have a point of concurrency called the circumcenter. And I'll explain why it's called that. It's a weird name. Circumcenter. Now, guys, it has to do with drawing a circle on the outside of this triangle, which I'm not very good at doing, but that is called a circumscribed, very dangerous word to say, circumscribed circle. It is circumscribed on the outside of that triangle, meaning it hits on all of the outside edges. And that circumscribed triangle is going to be equidistant all the way around from that center point, if you could draw. It's on the next page, so let's show you what it actually looks like. Here's a picture of what it looks like if you could draw like a normal person. Obviously, they can draw better than I can. So, what happens with the circumcenter theorem is whenever you have perpendicular bisectors, again, what is it out of the definition you need to get that's important? First of all, it's perpendicular bisectors. You got to see these little lines and you got to see the little right angle symbols. If you have perpendicular bisectors, then you have a circumcenter. In this case, what point would be the circumcenter in this picture right here? It's a point, guys. What point is the circumcenter? E. E is your circumcenter. It's where those lines all cross each other. Okay? It's where this line and this line and this line all intersect. Those are all perpendicular bisectors. They intersect at point E because they're going to ask you, what point is the circumcenter? It's point E. It's that simple. That's all you got to tell me. The one thing you got to know from this is it creates something special. Now, y'all know that they love big fancy words in geometry, so you need to know this word. We've used it before. Is equidistant. Equidistant to the vertices. Equidistant to the vertices. That's, I think, a vocab on your next test, so please, you got to know this. If it is a circumcenter, it is going to be equidistant to the vertices. See these little red lines right here that are dashed? These are from the circumcenter to the vertices. See how they all hit the outside edge of the circle and they're all the same length? That is always going to happen when you have perpendicular bisectors. So if you have a circumcenter, it is going to be the same distance to all of the vertices. Why does that help you, or what would you use that for? If you were trying to find these missing information and you see that these are all perpendicular look, guys, right angle symbol, congruent, right angle symbol, congruent, right angle symbol, congruent. That means E is a circumcenter, which means all 3 of these have to be the same. They are equidistant to the vertices. Which means I can set the ones with the same variable equal to each other. So I can set 4x plus 3 equal to 3x plus 6. So I'm going to minus 3x, That makes it x plus 3 equals 6. Minus 3, and x equals 3. Now, that gives me one answer. If they also wanted me to find y, how can I do that? Plug it in. Plug it back in. So it's going to be 4 times 3 plus 3 is going to be 12 plus 3, which is going to be 15. Now that's my distance right here. But is that going to give me my y? Well, what can I do now? What can I set my 2y plus 1 equal to? 15. That's exactly right. We know how long these all are. They're all the same, and they're all going to be 15. So we solve that. To solve that, we would minus 1, 2y equals 14. We divide both sides by 2, which means y equals 7. Perfect. Okay. So far, any questions? Okay. Like if I'd have plugged it into the other one? Nope. Gives you the same answer. That's a very good question. Nope. Now, I can't start to find them with the others because the two that have the same variable are the ones I have to start with. See how these both have an x? So I got to use those two first. It wouldn't help me to set one that has an x equal to one that has a y. It's a good question. Okay, here we go. Guys, this is what the problems are going to look like. They're going to be like multi-step questions. I'm going to show you how to do this so it makes it really easy. If you will do all the work ahead of time, the problem itself, like answering the questions, is going to be the easy part. So, they tell you they're perpendicular bisectors. Guys, if they are perpendicular bisectors, then this side is going to be congruent to this side, so it's going to be 16. This side is going to be the same as this side, so this is going to be 12. This side is going to be the same as this side, so this side is going to be good. We know that because they're perpendicular bisectors, these are all going to be right angles. And we also know that the circumcenter, which is point G, that's your circumcenter, it tells you, that is going to be equidistant to the vertices. So that means this piece right here is going to be the same as this piece right here, is going to be the same as this piece right here. So how long are all three of them going to be? They're all going to be 20, guys. Good. You've done a lot of work to get a lot of different measurements, guys. When you have all that, then filling all these in will be very quick. So let's go through and see if we can figure out how long each one is supposed to be. So AG, A to G is going to be 20. You've already found that one. BD is on the outside right here. You already found that. That's going to be 16. BD's out here. CF, same thing. It's out here. You've already found that one. So that one's going to be 19. ABO. Now this, you do have to do a little more math, a little more arithmetic, but AB is just taking those two pieces and adding them together. So if it's 16 and 16, the whole thing would be 32. CE, we've already found. CE is right here. We already did that part, so that one's going to be 12. AC, again, it's this whole thing. How long is AC? It's 38. Awesome. 38. See how it was really easy to go through those once you did all the numbers on the picture? Oh, and guys, what do you know? What kind of angles are formed by perpendicular bisectors? How big is ADG? This is a right angle, so how big is it? 90 degrees. The last thing says that BG right here is 3x minus 13. So what are we going to set that 3x minus 13 equal to? 20. It says it right on there. BG is 20. Because of that, we solve that by adding 13, adding 13. 3x is going to be equal to 33, which when you divide both sides by 3, means that x equals 11. Are they looking for x or to plug it back in? X. Since they only want x, all you do is put 11. Okay. Anybody see anything they need to ask about yet? Questions? We doing okay? Okay, are we on the back now? Mm-hmm. Okay, so on the back side, we do the other type of point of concurrency that we're going to deal with right now. There are two, like I said in this first half, there's a total of 4. Now, the other item that we dealt with yesterday were angle bisectors. So for angle bisectors, they have a point of concurrency also. So this is going to be angle bisectors, so do something to highlight star, understand that we're talking about the point of concurrency for angle bisectors. It is always going to be inside the triangle whenever you have these angle bisectors, and you know how to recognize angle bisectors. They're marked congruent on either side. It's got a line down the center. That is called the in center. Because it's in the center, guys, not so complicated. In center. For angle bisectors, it is called an in center. Now, just like perpendicular bisectors, there's one special thing about it that comes from that theorem that they've got for it. It's exactly like it was before with a little bit of difference. So when you have angle bisectors, again, that's what we're talking about, angle bisectors, they are going to create a point of concurrency called the in center. They are also going to be equidistant. There's that word again, equidistant. But this time, instead of being equidistant to the vertices, they are now going to be equidistant to the sides. That's the big thing. They are going to be equidistant to the sides. So this piece is going to be the same as this piece is going to be the same as this piece. How do I know these are angle bisectors? Because they're all marked congruent to each other. That's how I know that this is going to be an in center. And I know that each one of these pieces is going to be the same distance. So GE is going to, why the E floated down here? Some guys, you might want to move it closer. I don't like that being floated way down there. Sometimes when you move the pictures around, they do that. But that E is going to be GE, GF, GE, FE, and BE are all going to be equidistant to that center. Those are all going to be my pieces that are going to show that distance being the same. Which means when you come down here and you see these angle bisectors, see them all the way around, you know it's going to be equidistant to the sides. So which two are you going to set equal to each other? Perfect. Exactly. 3x and the 5x minus 30. Okay. This is one of those old algebra things that I'm worried about, so please listen. When there's only variables on both sides but numbers on one side, people tend to have an issue. Which one are you going to move? I'd move the 5x so that you don't end up with a 0 on one side. Even though the 3x is smaller, I'd move the 5x. That makes it negative 2x equals negative 30. And when you divide by negative 2, which y'all see the negative takes care of itself, and x equals 15. Just like we did before, in order to get this y, we're going to have to plug this 15 back into one of them. It doesn't matter which one, you get the same answer. So I'm going to plug in the short one. 3 times 15 is going to give us 45. Perfect. So all we do then is set the 4y minus 1 equal to the 45. So from there, add 1, 4y equals 45, no, 46. Oh, it's going to be a decimal, isn't it? Is that what it is? 11.5. Nice. I thought it was going to go down to 44 and divide evenly, but it went up instead, so it ended up being a decimal. Nice. Okay, anybody see anything before we do our last problems? Our last problem involves the same idea as we did before. It's kind of like, if you'll go ahead and do the work on the front end, it makes the problem a little bit easier. Okay. This is what they'll kind of look like as you get to the worksheet. Guys, I would use your notes when you're doing your worksheet today. This is what the remember, this is the one you're going to have the assignment on, because it looks just like it. It says, T is the in-center. If T is an in-center, then these are all angle bisectors. So this angle is the same as this one. This angle is the same as this one. And this one down here is the same as this one down here. That's important that you know that, because there's going to be questions about the angles in a second. And if they are, if this is an in-center, then PT, this piece right here, okay, QT, this piece right here, and RT are all, we just said it, they're angle bisectors. We also know that if it's an in-center, that it's going to be equidistant to the sides. To the sides, guys, not to the vertices, to the sides. So how long would ST be? How long would ST be? I didn't hear. No, ST is this segment right here. It's going to be congruent to all three of these, so how long is ST? 16. And then TU, this piece over here, same distance, guys, because they're all three the same. That means we would set 4x minus 4 equal to that 16. We would solve that equation by adding 4. Makes it 4x equals 20. Which when I divide both sides by 4 makes it x equals 5. Perfect. Okay, so the last thing for this set of notes is going to be take and do the angle stuff. So it says, I'm going to do these in colors, guys, because someone's going to mess this up. TRT, TRT is this angle. TRT, this piece right here, is 37. If this angle is 37, they want QRT, which QRT is QRNT. Guys, these have to be the same. It's bisected. So if this side's 37, this side's got to be 37. There's no work. You just got to know they're the same. Now on the other angle, the one they give you, I'll do in hot pink, is RPQ. RPQ. They give you this whole thing and they tell you the whole angle is 51. If they tell you the whole thing is 51 and they're looking for RPT, so they're looking for just this piece of it, how would I find just that piece of it? Yeah, just cut it in half because they got to be equal. And when you, it's going to be a decimal though. Is that what it is? Perfect. Thank y'all. 25.5. And there you go. Nicely done, guys. Anybody see anything they need to ask about? Yes. 25 near R. 25 was on that segment. So that piece was on this one right here, from R to T. It was there as a distractor because people are going to think maybe that instead of it being, these are all 16, then they're all three going to be 25. Because on the other one, remember, they were the same distance to the vertices. So it's there to mess you up. You don't use it. That's a good question. I love those kind of questions. Good. Anybody else? It's there as a detractor, they call them. Okay, then let's do this. Let me go ahead and end this so the recording will be there for them.